Oh, hello, my name is Karsten Kutzer. I'm working for Lenovo for the data center group. I came over as a lot of people in the data center group of Lenovo from IBM. And when I started working at IBM in 1995, I started to work for the so-called oil and grease department. I'm not sure if you know what the oil and grease department is, but it sounds like it's dirty work, and it was dirty work. It was the people that went down to the data center, pulling cables, plugging things together, so it was hardware. So it was considered dirty. And when I started working there, the first thing that I had to do with my colleagues was going to a data center and then dismantling an old IBM mainframe system. So we went to that data center, and I've never been in a data center before. It was really surprising. It was a large room, lots of racks, and then we found that IBM mainframe. And it was a really beautiful machine. It was 2 rows interconnected by a column, so it looked impressive. And then we opened the first side cover, and I was really surprised. It did not look like what I think a computer is. There was pipes, there was pumps, there was hoses in that rack. And I thought, okay, what's this all about? And the people had explained to me, okay, this is a water-cooled system. And I thought, why would you water-cool a system? And I talked to them, hey, my PC at home, it runs without water, it runs with electricity, in fact. And they told me, okay, the issue is we have a very, very high power density in this mainframe system. So they have that compute cells where the computation is done, and we have 300 watts on a very, very tiny space. And we can't remove that heat with just air cooling. We have to use water cooling. But they also explained to me, okay, this is old processor technology. That's bipolar technology, very, very fast, but very, very power hungry. So the next generations, that will be CMOS, and we will never, never again see water in the data center. Yeah, and that was the thinking at that time. And it proved that it's not true in the end. So we came back to water cooling in the year 2012, roughly, and there were reasons for that in the x86 space. We had data center limitations, so the power consumption of the CMOS technology or the processors was increasing, and at some point you can't really cool anything anymore with just air, or it gets really, really expensive to increase your infrastructure to do that. And then we also have increasing electricity cost, and I'm from Germany. It's really, really high energy cost that we're paying for electricity there. And so if you're looking at the total cost of ownership of a system, if you're just looking at, okay, it costs X million to procure that system, or it costs a couple of €100,000 to maintain the system with my employees, that's not the full story. If you're looking at the full cost, including the power, you will be surprised to see, okay, it's more than maybe 30% of the total cost in the end. And you can say, okay, it's not my department, it's not my budget, but maybe it's still a valid point to really look at the total cost of ownership of the system. So recently, we came across new effects. So the performance-power relation, I'll talk about that in more detail later, but power and performance, there's a correlation nowadays. So you get more power or more performance with more power. But there's nothing like, okay, you get more power just for free, more performance, sorry. Application diversity, there's another thing that we looked at. What we found is that not every application is the same as the other. Some consume a lot of compute powers, while others are more memory bound, and more compute power really doesn't help to improve the performance. And then, okay, we want to do something useful with the heat that we generate. That's energy, and we can blow it to the air, or we can do something useful with it. So this is here about the power-performance relation. What we saw back in previous years is that, okay, we get more and more performance over time, and the power consumption of the CPU was not really constant, but it was at an average level that was maybe 120, 130 watts or so. But since the Haswell generation, and also here with the new Skylake generation, we see if you want to really get more performance, we have to also increase the power. So the power budget for the highest CPUs has gone up to 205 watts, which is a lot. So there's a direct relation between performance and power. Application diversity. This is an example of a BQCD code. And it's the same code, and the only difference is what you're doing with that code. On the left-hand side, you can see a case that's CPU-bound. So you get 156 gigaflops from this code, and the node consumes about 500 watts. So what you also can do is you can find BQCD cases where it's really memory-bound. So you're consuming, in the end, 500 watts, but it's just 65 gigaflops. So now imagine it's memory-bound code. If you now decrease the frequency and thereby decreasing the power consumption of the code, would it really hurt your performance? And if it wouldn't hurt your performance, why not go down with the power until a point where it really begins to hurt? And then you're saving money and it's just for free. You're saving energy, money, and it's environmentally friendly without any cost in the end. And then, okay, what do we do with the energy that we are wasting? So this is a picture of a chiller that you have on your roof, and you sprinkle water on it, and you have your blowers at the top of your roof that suck air in, and thereby you're cooling the stuff, but the heat is really going away to air, and you do nothing useful with it. But you could imagine having a big data center and next to it a swimming pool, and you can just heat the water and make some use of that. If you're getting 50 degrees hot water from your system, you can easily heat the pools. Or you can use the energy for greenhouses, for example. That's just ideas. And the third thing, what we could do, and I will go into that in more detail in the end, is using it indirectly to create chilled water for other things that you have actually to cool. You can use the hot water to generate chilled water. For Lenovo, it's important to really understand and see what our customers really want to do. And talking to customers, then everyone really wants to be able to use the best CPU that fits his specific needs. And that starts with maybe low frequency and low power CPUs, but others want the high power, high frequency CPUs that consume up to the 205 watts. So we want to be able to provide that to the max TDP that's supported by Intel. We want to have the best performance by fully utilizing the system. So even if you have a 205 watt CPU in your system and it's air cooled and maybe the cooling is not sufficient, then the system will throttle down at some point. We don't want that. We want to get the full performance if we really need it for our applications. Then the best TCO performance is really thinking about, okay, how much energy do I have to invest to get to a result, and can I lower that? We want to use make best use of the unlimited data center capabilities, of course, and in the end, it's also about carbon footprint. There was a discussion a couple of months ago about, okay, how much CO2 is emissioned by a single search on Google Web. And the discussion was, okay, is it one kettle of water that you bring to boil, or is it less or whatever? But in the end, there is some resource consumption in everything that we do as a HPC community, and maybe it's worth just thinking about if we can improve that, especially if there's not a big cost associated to that. So there are three pillars that we're focusing on. Of course, Lenovo is a hardware supplier, and we are providing specialized hardware for this. But we're also looking at software that improves the power consumption of the system. And then we're also looking at infrastructure things that can improve power reuse or energy reuse. We start with the hardware. So in general, there are two cooling technologies that we provide that are water-based. That's first of all traditional rear-door heat exchangers that we provide. And then there's direct water cooling, and I will go into more detail about those two technologies later. So the traditional air-cooled thing is Okay, you have your rows of racks, you have somewhere in the data center, you have room air handlers for the room air. And that's an approach that really costs a lot of energy in the end. And you get some effects like hotspots in your data center that you have to control. So there are disadvantages of this technology. But of course, you have the widest application. You can use anything in your data center with this approach. If you want to be more sophisticated, you can put the rear door heat exchanger on each of your racks, and then you're cooling the air that was heated by the racks, and you get cool air back to the data center, which is nice. And then the direct water-cooled systems, you're trying to move the heat directly from the CPU, from the memory, from whatever is in the system to water, which is the most effective approach. But of course, it's not as flexible as the other ones. If you're looking at the additional cost for direct water cooling compared to rear door heat exchangers, it really depends on, first of all, if you're constructing a new data center. If you're starting on a greenfield, then you can just invest your money on the cooling infrastructure where you wanted to invest. And then you have, usually after 1 year, you get a break even where there's no cost difference anymore. If you are investing into an existing data center, then the break-even point really depends on how much the kilowatt hour costs you. So for 20 cents per kilowatt hour, it may be in a range of 2 to 3 years where you have a break-even of the cost. And this is based on TCO analysis that we made based on real customer numbers. The rear door heat exchanger, what can you achieve with that? You can achieve up to 27 degrees chilled water you can use for that approach, but the efficiency of this cooling approach really depends on the water temperature and what you have to remove. So chilled water, the rear door heat exchanger water-cooled version looks like this. You have just a passive backdoor, you have pipes, and you can remove up to 100% for a 30 kilowatt rack and up to 90% of the heat for a 40 kilowatt rack. And this is about where we are today with the most dense systems. So it's a reasonable approach really to remove the heat from the data center without dissipating that to the air. And this is what it usually looks like. You have your facility chilled water, you have heat exchangers, pumps, and that's all usually combined into a cooling distribution unit, and then you connect your rear door heat exchangers via hoses to that system. So the direct hot water cooling, we nowadays can cool up with up to 50 degrees inlet water. So the water going into the rack can be up to 50 degrees. That depends on the configuration of the nodes. For some where we have hard drives, for example, it's maybe just 45 degrees, but it's really very high temperature. And the outlet temperature can be like 56 or even 60 degrees Celsius. So you have some reasonably hot water to do something useful with it in the end. We're removing up to 90% of the heat directly to water. The rest goes to air in the end. Yeah, and we have, you can see it here, more than 24,000 of those direct water-cooled nodes over the several generations as installed base. So we have a history since 2012 and several generations. So it's a very proven technology, and it's in mass use. So it's nothing like it's invented yesterday and we'll see if it works tomorrow. It's really proven technology. So this is our latest system. It's the SD650, codenamed OceanCat. You can see here, this is a tray, and 6 of those trays go into such a chassis. And this is essentially the backside of the chassis, where you have the water hoses coming from below the rack usually, and then the water flows here through the dual compute node. And we'll have a second picture of that describes that in more detail. We can have InfiniBand on those nodes. We can have OmniPath on those nodes. We can have disk drives on those nodes. So it's a relatively good flexibility, but it's not like a 2U server where you can have 24 hard drives. It's, yeah, it has some limitations in the end. So here you see from the back end of the rack, from the chassis, you get the 50 degrees Celsius water inlet, and then this water inlet is split here to the second node. So we have one node here, the second node here, and then the chilled water flows through the CPUs and also across the memory DIMMs and also across the disk drive that is here. And here's the adapter that's also cooled via this water flow. And then the water goes back here with maybe 60 degrees Celsius. So it's a very, very sophisticated design, and it works very, very well. And it has been, as I mentioned, improved over the last 6 years over time. This shows some more details. What's really important is, okay, we wanted to have very, very high inlet water temperatures, and how do we achieve that compared to the previous generation? What you want to have is a relatively low delta T between the CPU and your water. So the lower the delta T, the higher the temperatures can be. And that's also true for the memory and the network adapters. That was one step further beyond what we had with the previous generation. Then there's cooling of hard disk drives also that is now included in the system, which we didn't have before. So we have a cold plate here, a conductive plate that's cooled with water and essentially can cool the disk drives. So that's another advancement. This here is a picture that shows us a typical LinPack run on such a system. So there was a discussion of how much value is LinPack in nowadays world. I think it's very important still at least as a tool to demonstrate what the system does under very, very high power load. And that's really a stress test for the system. What you can see here, when the system starts up, you get very, very high CPU frequencies in the beginning. So it's pushed up to a peak with non-AVX instructions, and then at some point the AVX instructions start, and then the frequency drops a little bit. The power consumption, there's also a peak in the beginning, and then we go to a constant TDP. And you can see here, this is one CPU, and the colder CPU is the one that the water flows through in the beginning. So it's very interesting to see that, you are very, very constant here at the temperature level. There's no big decrease, increase. It can keep on forever, essentially, with this water cooling, compared to air cooling, where you may see some decrease over time. So what could you do besides saving energy? You could also boost your performance if you want to. So this is the air-cooled system, same CPU compared to the water-cooled system, and you can get up to 10% more performance from the same CPU. The only difference is air-cooled versus water-cooled. And the reason you can see here you have a CPU temperature of 80 degrees, and here it's just 36. So very, very efficient cooling. In this case, the inlet water temperature was 18 degrees Celsius. So we can't just do very, very hot cooling. If you want to improve performance, you can also use chilled water to boost your performance. The drawback is that the power consumption will go up by almost 20%. That's the drawback that we have. The software side. So we're looking at two things. First of all, reporting. So you have to understand what your actual power consumption is to do something like chargeback or actively going to your application and changing things like frequency. The more accurate your measurements are, the better the decisions are that you can make. And then, of course, you need some kind of management to implement those decisions on the applications. What we implemented with our ST650 systems is a very, very high frequency, very accurate measurement that provides 100 Hertz, very accurate power reading compared to what you have with the traditional systems. In traditional systems, you have an error rate of maybe 5 or 6% even, also with the REPL interface. Here we are down to 2 to 3%, which is rather important to really have good data to make your decisions. This explains what we actually do with that data. We have the DC power readings, of course, that I mentioned, which are very accurate, but we also now have a DC energy meter. So we are measuring on the hardware the energy in joules. And this is also very important because otherwise you would have to pull that information from a higher level all the time. This way you have a reading at the beginning of a job and a reading at the end of the job, and you understand how much energy was consumed during the runtime of the job. And that at very, very high accuracy. And that was also very important for us. So what do we do with this information that we receive from the hardware? We're trying to optimize the frequency that the applications run with compared to the performance gains that we get from that. So what we invented together with Barcelona Supercomputing Center is the Energyaware Runtime. The motivation is, of course, energy and power is important, we know that. And also we found that the performance really is not depending necessarily on the CPU frequency, but also on the application. We have applications that can run with almost same performance with very, very much lower frequency and much lower power consumption. So the challenge, though, is how do I find the best frequency for an application? So a user starts a job on your system, and how would you know if that application would benefit from higher frequency or not? And that is the challenge that we are addressing with the Energyaware Runtime. So what do we do with Energyaware Runtime? First of all, we are characterizing the architecture of the system. So the node, memory, which type of CPU we have in the system, and how does it behave. Then we have characterization also of the application itself during runtime. So how does it feel like? Has it a high memory bandwidth usage or not? And then we're doing a power and performance projection. So how would this application run if we lower the frequency compared to what it's running right now? And we have two policies defined. First policy is minimize energy to solution, where we're trying to lower the frequency up to the point where the application is going to be hurt by the low frequency. Or you can do it the other way around. You have a default low frequency, and then you increase that frequency and see, okay, what happens if that application gets a higher frequency compared to what it had before. So that's implemented in two phases, essentially. We have the learning phase at the beginning of the system implementation, or when the system is implemented. Then we collect the application characteristic of the system by itself by using some standard kernels, calculating coefficients, and they go into a database. And then during the execution of each individual application, this application is triggered or scanned for what it's actually doing. We're detecting the outer loop of the application, and we see during that loop iteration how is power and performance consumed by that application, and then we're calculating the optimal frequency for that based on the energy policy that we defined up front. And then after a few iterations of the application, it's scanned again for, okay, did our prediction work or did it not work? And then we maybe change again. And in the end, we get an application that runs at an optimal frequency for what it's supposed to do. And we can see that here in an example, BQCD. We have an MPI rank 0. Here on the right-hand side, it's MPI rank 8, just to see that it works across several nodes. We are detecting here the big loop, so the outer loop of the application. And at this point, we are reducing the frequency from 2.6 gigahertz to 2.4 gigahertz. And we see immediately that the power is reduced from here to here, and it's the same power consumption across all the MPI ranks in the end. And the iteration time of the outer loop doesn't change significantly, although we really reduce the power consumption. And that's the benefit of this runtime in the end. So coming back to infrastructure, there are several metrics that are common to talk about how efficient is a data center. We have the power usage effectiveness. We have the IT usage effectiveness, which tells us how efficient is an individual system compared to others. And new is the energy reuse effectiveness, where we are taking into account that we may be able to reuse some of the power that we're actually consuming. And this improves the ERE factor. Ideally, if we reuse 100% of the power, the ERE would be 0. That's something that we would never achieve, but that would be the goal or the target, long-term target. So besides all those cooling technologies, we are now looking at something else, which is direct water cooling with adsorption chilling. Adsorption chilling is a technology that allows us to create chilled water from hot water. And how does that, or what's the impact? If we're just looking at direct water cooling, we have some advantages from lower power consumption per node. We don't have fans, for example. Yep. 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 Yeah. It's more or less the, it's like a modification to the PUE.
It's effectively takes the PUE all the way down to 0.
Yeah.
Reuse everything after considering the infrastructure.
Yeah. So PUE, the idea is you're using additional power besides your computer system to drive everything. And here we're using the same thing, just we're subtracting the reused power. And ideally, we would reuse 100%. So if we're moving all the power to the swimming pool, then we're fine. So this was an example here, a calculation, what could be the total saving. It's like 35 to 40% if you take into account all the things that you can do to improve your power. And this has more or less been proven by previous generation systems where we get to exactly those numbers. And we're now going beyond that with the adsorption chiller. And I'm not sure if anyone is familiar with the concept of the adsorption chiller. I just try to explain it a little bit. So we have a vacuum container here. And the vacuum container, we have water. And the water evaporates in the vacuum at reasonably high temperature. And this creates cold. It consumes energy. So it chills down here this heat exchanger and the water in this heat exchanger loop. So we have 23 degrees Celsius water inlet, and that gets cooled down to 20 degrees Celsius just by the vaporization of the water. And the vaporized water, it moves over here to the second part of the chamber. And there here we have the adsorber, which is usually silica gel or zeolite. And the water just sticks to that adsorber, and that creates heat in the end. So we're heating up the heat exchanger in this part of the system. And this goes to the point up to where the adsorbent really has consumed 100% of the water that it can consume, and then the process just stops. Then we have a balance. Therefore, we have in the same adsorption chiller a second chamber, which is really identical. And this works at the same time, just the other way around. What we see here is we have desorption. So we're bringing in hot water, and that starts to vaporize the water that's bound here. And this vaporized water goes back here, and here on the colder heat exchanger compared to this side, it gets condensed again. So what you see here is we have essentially 3 loops. We have a chilled water loop. We have a hot water loop. This is where the compute racks are, in essence. And then we have a medium temperature loop that shows up here and here. And those loops are essentially combined together. Those 3 loops, this goes up to recoolers on your on the roof. And this goes to your storage or whatever, and this comes here from your compute racks. So it's a very nice way to create chilled water to drive your infrastructure. And this is supposed to drive the savings up to 40 or even 50%. And that's the target that we have to achieve with this technology. With this, I'm at the end of my presentation. Any questions from your side?